I'm going to talk about strength in this lesson. I will start with basic concepts, then move on to the displacement field, and finally the strain tensors. When an object is deformed, it usually changes shape and size. Strain is a measure of the degree of such changes. When a line is deformed, the change in its length can be measured by the following linear strains or longitudinal strains. Elongation, or simply strain, is defined as change in length divided by the initial length. The initial length here is represented by L0 and the final length LF. The change in length divided by the initial length gives the elongation. A second measure of linear strain is called stretch, which is defined simply as the ratio of the final length to the initial length. Stretch is related to elongation by this relationship. Sometimes it's easier to speak of the square of the stretch. That is called quadric stretch. In a folded situation, the elongation is a negative value because the length is shortened. In the situation of a Booleanized structure, the line here is stretched. The final length is greater than its initial length. In either extension or shortening, stretch is always positive. When a line is shortened, stretch is less than 1. When it is extended, stretch is greater than 1. There is also a fourth measurement of linear strain that is called natural strain. Natural strain is defined as the natural logarithm of stretch. So natural logarithm of final length divided by initial length. It may appear a little bit obscure why a strain should be defined as the natural logarithm of something. We can understand this definition by considering this case. Imagine a line is progressively lengthened, so progressively stretched or shortened. Its initial length is L0. After the first increment of the stretch, the length is changed to L1. So the first increment of the strain is L1 subtract L0 divided by L0. In the second increment of strain, the length is changed to L2. L2 subtract the length to start with, that is L1, divided by its L1, that's this. We can carry on this increment by increment until we reach the final length. We add all these increments together, we get the total accumulated linear strain. However, in this situation, since the initial length changes, it's not going to be the same as the total elongation. In fact, we can consider the process as continuous. So the incremental strain can be infinitesimally small. So there is an infinitesimal change in the length divided by the length at that time. That gives the infinitesimal increment of the strain. Integrating all the infinitesimal increments gives the finite strain. And this is natural strain. So when strain is large, natural strain is a very good measure. When the strain is small, so in the limit, the elongation is very small, then using this mathematical limit relationship, natural log 1 plus e is approximately e as long as e is very small. So for infinitesimal strains, elongation is the same as natural strain. Distinction between the two disappears. Deformation also changes the angle between lines. That is the concept of shear strain. In this diagram, the little cabin has been deformed. Originally, this vertical edge and the horizontal line were orthogonal, and now the angle between the two deviates from 90 degrees, and the magnitude of the deviation is the shear angle, and the shear strength is defined as tangent shear angle. So shear deformation, shear strengths are commonly observed in geology. Shear strengths can be defined for all lines in a continuous deformation. In these 2D examples, it schematically shows the shear strengths of different material lines. On the left, it's a rectangle in the undeformed state. On the right here, it's the deformed state of this rectangle. Material lines generally change orientation and length, and the length change is measured by longitudinal strengths. Consider a few material lines like C and D were two sets of lines initially orthogonal to each other. They are no longer orthogonal to each other in the deformed state, and the shear strength for each line can be defined. So the shear angle for line C is this, psi C, because D was orthogonal with it. In the deformed state, D is rotated with respect to C, and the amount of rotation is psi C. Line D also has a shear angle. C was orthogonal with it in the undeformed state. C is now rotated counterclockwise for the amount of psi D. So, the shear strength for line C is this, gamma C, and the shear strength for D is gamma D. Because C and D are a pair of orthogonal lines in the undeformed state, their shear strengths are equal in magnitude, but opposite in sign. Now, we understand the strengths of individual lines, longitudinal strength or shear strength. How do we extend this concept to three-dimensional deformation? How do we find a measure that can describe the strength of a continuous body? To do that, we need to use mathematical tools. First, we need to have a coordinate system. We need a coordinate system in which every material particle can be defined by a location, by a position vector. Here we use Cartesian coordinates x1, x2, x3, and their base vectors e1, e2, e3 respectively. The undeformed state is schematically shown here. The geometrical state of a continuous body is called a configuration. So, undeformed configuration, or called reference configuration. When this body is deformed, so it generally changes position and also changes shape, it is called a deformed configuration. With this coordinate system, we are able to give the position of every material particle in the reference configuration, and we will use the capital X. So X is OP. P is a material particle in the reference configuration, and OP is the position vector for that specific material particle. Now this same material particle is moved to O lowercase p with a position vector lowercase x. It's a new position vector in the deformed configuration. So the changing position vector of a material particle from reference to deformed configuration defines its displacement vector. So in the general case, displacement varies in space. We say they define a displacement field. Every material particle moves to a new position, and there is a one-to-one correspondence between lowercase x and capital case X. There is a one-to-one relationship, and this relationship can be written as a function. So little x is a function of capital X, Or in reverse, capital X is a function of lowercase x. Now with that setup, we can now talk about displacement and displacement field in more detail. We want to find a strand measure that can describe the linear strand of every line. So we need to consider a small segment, small line segment in the reference configuration. We want to find a general mathematical description of this. If we found this, then it is going to be a definition we are looking for. So with this setup so far, we have displacement. Displacement generally varies in space, so we have displacement gradient. The gradient can be expressed in terms of the deformed coordinates, that is called Eulerian displacement. The gradient can also be expressed as a variation in the original coordinates, that's the Lagrangian displacement gradients. So, we want to look for a mathematical description of this. We can do this from a little bit mathematical derivation using calculus. As we explained in the previous slide, the displacement can be expressed as a function of the deformed coordinates, or in terms of the undeformed coordinates. These two relationships are just a recast of this. The top is Lagrangian and the bottom is Eulerian. We can write the relationship between d little x and d capital X using this. This is a calculus, differential of a function. Alternatively, we can express d capital X in terms of d lowercase x. So from the top, this relationship to these two relationship is just the application of differential calculus. So the quadratic line length of dx can be expressed this way. This is again just the plug-in of this relationship here. So expanding this relationship gives us this relationship. The quadratic length of the initial segment is this. So the change in quadratic length is this. So this relationship should capture the strand information. You can appreciate why the quadratic length change is actually very much the same as this concept, the strand concept. If the strand is small, so ds, d capital S or d small x is small, it have this relationship. So in the end, this is actually, see the length change, ds subtract ds, that is here. It's dx subtract dx, the length, divided by initial length. That's the concept of strand. So this actually captures the strand of the line segment. We can do the same derivation here, expressing everything in terms of the deformed coordinates, and we arrive at a relationship like this. Now, these two expressions contains the information of strand. So they give rise to the definition of two strand tensors. One is called Eulerian strand tensor, and one is called Lagrangian strand tensor. Here is another effort. I try to use two-dimensional explanation using the geometry to explain the concept. Basically, we want to understand the length change, that is the strand of an infinitesimal line segment. A and C are infinitesimal line segment in the undeformed state. Imagine a rectangle ABCD in which AC become a diagonal line. Now in the deformed state, ABCD becomes small abcd. It's a red parallelogram. And the infinitesimal line segment, capital AC, is transformed to lowercase ac, the dashed line here. We want to find out the relationship between their length. We can write down their coordinates for A and C. Again, we use capital letters for the coordinates in the reference. So the coordinate of point A is capital X, capital Y. B is capital X plus D, capital Y, X, Y. So Y is the same, X is increased by a small amount, and so on for C and D. This capital A is moved to small a here. The coordinates is this, because X is increased by displacement in the X direction, Y is increased by displacement in the Y direction. We can do the same thing for coordinating C. Again, we use a little bit mathematics, calculus. We get these coordinates expressed in terms of initial coordinates, the undeformed coordinates. Now these two gives a relationship between the initial line segment dx dy and the final line segment dx dy. The relationship is expressed here. Now the quadratic length of AC squared using Pythagorean theorem is dx squared plus dy squared, which can be expressed in this relationship. This relationship is what we obtained in the last slide. The new length AC squared is this. We can plug this relationship into this and we get this relationship. The quadratic length change AC squared subtract AC capital AC squared gives rise to this relationship, and this is explicitly the Lagrangian strength tensor we obtained previously. So finally, we get two strength tensors, finite strength tensors, because these tensors are applicable to large strengths. One is Eulerian strength tensors, which is this relationship, and the second is Lagrangian strength tensors. If the deformation is small, if the strength is infinitesimal, then these terms, the third term in either of these equations, these definitions, can be neglected. So, in infinitesimal strengths, the strength can be defined as the linear part. That is called the Cauchy strength tensor. In elasticity, strengths are small, so the Cauchy strength tensor is used. With the Lagrangian and/or Eulerian strength tensors known, we are able to calculate the strength of any line segment in the body. By definition, the Lagrangian strength tensor is defined by this equation. Divide this equation by d capital S squared. The first term becomes the quadratic stretch of the line segment, and the second term becomes 1. The right-hand side becomes this form. Now the terms in the bracket d capital Xi over ds are components of the unit vector parallel to d capital X. We get the formula to calculate the quadratic stretch of any line segment as long as we know their orientation by its unit vector. Alternatively, we can use the Eulerian strength tensor to calculate the quadratic stretch. Definition of Eulerian strength tensor is by this equation. Now we divide both sides by d small s squared. The first term becomes 1. The second term becomes 1 over quadratic stretch. The right-hand side of the equation becomes this form. Now the terms in the bracket dxi over ds are components of the unit vector n parallel to d small x. Therefore, we arrive at the formula to calculate the quadratic stretch of any line segment as long as we know their orientation given by a unit vector. When the strength is very small, for infinitesimal strength, we have the relationship here. The infinitesimal strength tensor is the symmetric part of the Eulerian displacement gradient. The anti-symmetric part, that is this, is actually the infinitesimal rotation arising from the displacement field. In many textbooks, they explain the geometrical significance of this relationship. Here I use the example of a simple shear to explain this concept. So the black square is deformed into the red dashed parallelogram by simple shear. So the total deformation gradient is this. This deformation can be considered as a pure strand, which is represented mathematically by this. So that pure strand deforms the black square into this green rhombus with a rigid body rotation that is described by omega. That's this. The green rhombus will become coincident with the dashed parallelogram. Therefore, the simple shear deformation, the infinitesimal simple shear deformation, can be regarded as a pure strand plus a rigid rotation. That's the physical interpretation of infinitesimal displacement gradient. The couch strand tensor is very much like the couch stress tensor in that it is symmetric. It has three principal strands and principal strand axes. And like the stress tensor, the couch strand tensor can be decomposed into a volume strand and a deviatoric strand. If the volume strand is 0, we say the deformation is isochoric or constant volume deformation. Ductile deformations are generally assumed to be constant volume. If a material deforms without volume change always, it is said to be incompressible. Similar to the deviatoric stress tensor, we use a second invariant of the deviatoric strand tensor to measure the effective shear strength. So the effective shear strength is taken to be the square root of the second invariant of the deviatoric strand tensor. Okay, that's it for my introduction to the strand. More about strand will be discussed in the flow and deformation section of this course. Thank you for your attention.